Thus far in statistics and probability, we've talked about descriptive statistics and inferential statistics, where we've described and then maybe predicted or inferred information about a population given a sample. However, all of those things really only dealt with one or two different parameters or one or two populations. In the real world, however, many problems are actually characterized by multiple and possibly interacting parameters. So we want to understand if there's a relationship between the parameters, and if so, how we can approximate or describe it mathematically. Modeling techniques are used to develop relationships between parameters to better understand the behavior of different systems. We've talked a little bit before about different types of models, so let's review the ones we have discussed so far. First of all, there's the mechanistic model. And if you remember, a mechanistic model is derived from a known description of a physical mechanism. Something we use as an example for a mechanistic model was by knowing, like the laws of physics, we could predict the patterns of the tide. Then there's an empirical model, and an empirical model is derived from an analysis of collected data points that are good approximations of a physical mechanism for which a well-defined description has not been developed. So we go out and collect all these data points and we try to come up with a relationship to explain them. So if you remember, the example we gave here is if you sat on the beach for months and months or maybe years and years and you observed the patterns of the ocean and the tide and how far it came in over and over again, and then eventually you could predict that just based on what you're watching. So both of these models can be used in design. However, in this chapter we're going to focus on empirical because that's what you'll see most in your research or in your career, is coming up with some pattern or relationship that hasn't been discovered or described by anyone before. Something we first need to talk about is how we can model variation. So obviously not many things are going to have a perfect relationship one to another. So here, let's first talk about a random variable, and this is that formula that we saw previously, where we called x a random variable and we described that random variable by mu plus epsilon, where mu is the constant or the average value, and epsilon then is my variation, my noise, or my random disturbance. So epsilon basically describes why things are different or why things aren't all just the average value. So we also sometimes think of this as our error. So in this chapter we will just continue to build on this formula of the random variable. So as we get started, we're going to talk about the difference between deterministic versus statistical modeling. So oftentimes models are deterministic in nature, and what that means is that we have an exact formula for relating one parameter to another. So an example I like to use to make sense of this to me is a rental car price. So suppose the price to rent a car is $25 per day plus 10 cents per mile driven. So the miles then driven are the independent variable and price is the dependent variable. We might not know ahead of time how many miles we will drive, but we can always calculate an exact estimate of the price given any number of miles. So maybe you go to different car companies and you want to shop around for a rental car. You could compare these different formulas to each other based on an estimated number of miles. So with statistical modeling, we don't have an exact formula that we're going off of. So we need to use this so we can account for that variation or uncertainty. So in order to figure out a model for statistics, we use something called regression analysis. So it's a set of tools used to develop these non-deterministic models between two or more variables. And we will get into that right now. To begin our talk on regression analysis, we're first going to talk about scatter plots and correlation. So a scatter plot, or a scatter diagram that we did in the homework in chapters 1 and 2, is used to show the relationship between two different variables. So a correlation analysis is then used to measure the strength of the association or the linear relationship between the two variables. So here, within correlation analysis, we are only concerned with the strength of the relationship. So when we talk about the relationships one with another, here I'm going to say this is a linear relationship. So if I plot all my values and create a scatter diagram, this set of values closely approximates a line. And this one down here closely approximates a line as well, it just is in the negative direction. And over here, these don't necessarily approximate a line, but they do approximate a curve or maybe some kind of polynomial function. Okay, so when I talk about strong and weak relationships, this is what I'm talking about. So here you can see how these right here kind of clustered together, or they're close together, all those points kind of within these two dotted lines on the outside. Once again, these are kind of all clustered together within these dotted lines. But these over here aren't really grouped tightly together. They're kind of spread out. So that infers then a weak relationship between my x and my y variable. Versus these over here are pretty closely related. So I would call the relationship between x and y a strong relationship. So we use regression analysis to predict the value of a dependent variable based on the value of at least one independent variable. And when I talk about this, the x is going to be my independent variable and the y is my dependent variable. And that makes sense because if you think about a function, I always change the value of x, and then the y value, or the f of x, will then change based on the x. So here we also then will use it to explain the impact of changes in an independent variable on the dependent variable. So the dependent variable is the variable we wish to explain, and here that's always going to be your y value, and my independent variable then is the variable used to explain the dependent variable. That then is going to be my x value. Okay, so as we start the regression analysis, we're going to begin with a simple linear regression model. In this type of model, we only have one independent variable, x. And the relationship between x and y is described by a linear function. So we're not looking for a polynomial relationship. We're not looking for an exponential relationship. We are trying to solve for a linear relationship. Meaning that when I plot these in a scatter diagram, that scatter is going to be best represented by just a line. Okay, so the changes in y are assumed to be caused by the changes in x. So if we plot these as scatter diagrams and then draw a line through the very middle of them to most accurately represent what that relationship looks like, this would be a positive linear relationship, a negative linear relationship, and this one right here is not linear. See how it's kind of exponential? So we would not describe that with a simple linear regression. And down here, we would not describe this with a linear relationship either, because this slope here would be 0. A population linear regression model, or a simple regression model, this is what the formula would look like. So this really is no different than what we showed in our previous video, where I have y equals mu plus epsilon. This time I just have these beta factors taking the place of my mu. So if I look at these values right here, I have x being my independent variable and y being my dependent variable. That's really nothing new, so let's move on. So this beta naught is just going to be my population y-intercept, and this beta sub 1 is going to be my population slope coefficient. So if you kind of look at this right here, really I have some value times x plus something else. It looks awfully familiar to y equals mx plus b. So this would be my b, or my y-intercept, and this would be my m, or my slope. And then this epsilon over here then would be my random error term, or we refer to it as my residual. So that value would then explain the variation in the model. So like we said, that describes the line itself, so mx plus b, and that is my random error. Okay, so as we begin this regression, we are going to make some assumptions. My error values, epsilon, are going to be statistically independent, so they are not related to each other. My error values are normally distributed for any value of x, and the probability distribution of the errors is normal. So there's an example of this in your book where you can go through and visualize how each of the errors, or the residuals, are normally distributed along any given x point. The probability distribution of the errors has a constant variance, and the underlying relationship between the x variable and the y variable is linear. As we get started, let's just kind of look to see how this works. So I have 6 observed values. So I'm going to plot those on just a normal Cartesian axis. So I have x and y, and I plot those values just at their respective x and y coordinates. So within this value, I then have an observed x value. So that's going to be right here, is just some x term. I is its respective term. So some value of x that corresponds to this data point right here. So that then has its corresponding, or its observed y value for that given x value. My goal is to figure out a line that most accurately represents this data. So I'm going to draw a line through that. Just to the best of my knowledge, I think that purple line most accurately reflects the middle of that data. Okay, so then I can find the slope, just my rise over my run, right, like this. And then my intercept then would just be where this crosses my y-axis. So then based on that, I now have some predicted values. So I am saying that this purple line right here is now kind of my predictions of this data set. So you can interpolate, meaning find a value maybe right here that's not necessarily within my data set, but I would be able to predict its y value because for this x value, I now have a y value. So for this x value right here, I can then come up with a predicted value of y based on that. So here, the predicted y value would be right here rather than its real value, which is up here. So to incorporate that then, we call the distance between my actual or observed value and my predicted value a random error for that x value. So that is the error. That describes the variation in the line. And then we describe the whole equation of the line with this beautiful equation right here. So this line is described with this formula, y equals beta naught plus beta 1x plus epsilon. Okay, so let's look at this with maybe some data. This is some data that's found in your book. So I have the salt concentration in surface streams and roadway areas. So maybe someone thinks that there's too much salt found in streams, and maybe it's getting there from roadways. So they want you to go take samples. So I go out in a specific area and I take 20 different samples or 20 different observations. And first of all, I have this x value, and that's a roadway area. So some squared distance, and then this is my salt concentration, or how much salt is found within that given area. So I'm then going to graph this data. So that looks like a pretty strong relationship, right? Those data values are all pretty clustered together like this. So then if I want to come up with a model or a linear model for that data, I'm going to draw a line right down the middle of those values. So that line then could be represented by y equals beta naught plus beta 1x plus epsilon. So here, the error term for each data point is called my residual. So this e down here is similar to this epsilon. So we called this value epsilon before with this equation as being the distance between the dot and the line, and that is just what E is. We're just going to call it from here on out a residual. And a residual then can be found by the distance between the observation itself and the equation of the line. And once again, the hat just means a predicted value. So the equation of this line is a y hat. So sometimes these residual values can be positive because we're going to have my observed value being above my line. So I would say this value minus the line would give me a positive distance. But if I were to look at the distance from this value to the line, this minus the equation of my line would give me a negative value. So residuals can be positive or negative.